Hello everyone, and thanks for watching Edupedia World Videos. In this video, we further our discussion about the properties of matrices. Now let's take a small recap of what we've learned so far. Matrices are basically arrays of numbers It's actually more general than that. They can be arrays of variables or even arrays of functions or complex numbers. But for our course, they are just arrays of real numbers or variables representing real numbers. Right. And so they'll be represented with square brackets. You'll have some term like 1, 2, 4, 6, 1, 9, 2, 1, 6, 4, 6, 7. This would be a 4 cross 3 matrix because it has 4 rows and 3 columns. All matrices are rectangular. If the number of rows are equal to the number of columns, like a 3 cross 3 matrix or a 4 cross 4 matrix, then it's called a square matrix. Then we learned how to have equality of two matrices. Two matrices are equal if their size is the same and their corresponding entries are equal. So if you have, let's say, A1, 3, 4 is equal to the matrix 3, B, C, D. If this is true, first of all, both are 2 cross 2 matrices, so you can easily see that that's fine. Then A has to be equal to 3, B has to be equal to 1, C is equal to 3, D is equal to 4. So two matrices being equal means that their size is the same and each corresponding entry is the same. Then we learned how to add two matrices. And that was simple enough too. If you have a matrix A, B, C, D, E, F, let's say, a 3 cross 2 matrix, and you add to it a matrix G, H, I, J, then you cannot do that because you cannot add two matrices of different sizes. But if you had another row here, K, L, then these two matrices could be added and the sum would be a matrix of the same size in which each entry was the sum of the corresponding entries. So the first term would be A plus G, the second term would be B plus H, the third term would be C plus I, and so on. So this is addition of two matrices. Then we saw how to multiply a matrix by a scalar. And that was quite intuitive too. If you have a scalar which is a number, let's say 4, and you multiply it by a matrix A, B, C, D, all that needs to happen is you need to multiply this scalar to each individual entry. So this matrix would be 4A, 4B, 4C, 4D. Right. So this is how we multiply a scalar. Just a reminder of the notation for us. Small letters will represent scalars. Small letters with arrows will represent vectors and capital letters will represent matrices. Right. So this could be represented as K, A is equal to B, where K is the number 4, A is this matrix, B is this matrix. Now the next natural step is to understand how to multiply matrices together. And if you follow this pattern, which we've seen, equality of two matrices means corresponding entries are equal. Addition of two matrices means corresponding entries are added. Scalar multiplication means each corresponding entry is multiplied by that scalar. Then you would assume that matrix multiplication would be just as intuitive in that you just multiply corresponding entries. You would assume that you can only multiply two matrices of the same size, and you can what you have to do is multiply corresponding entries. So 2, 6, 1, 4 multiplied by, let's say, 3, 1, B, 4 would simply be 2 multiplied by 3 is 6, 6 times 1 is 6, 1 times B is B, and 4 times 4 is 16. This is what you would expect if you thought matrix multiplication followed the same pattern as did everything else. But this is actually not true. Matrix multiplication is defined in a somewhat complicated manner, and so before going into how matrix multiplication is defined, I'd like to talk about a couple of things. One of them is why we learn matrices in the first place. Right, there are many abstract mathematical structures which are not needed for the representation of numbers. After all, you could represent numbers just as a collection or as separate numbers. You didn't have to represent them in a box with square brackets. But the reason we created matrices was because they made a lot of calculations easier. They made a lot of problem solving more simple and reduced the number of steps. Right, so matrices are actually very useful because they can represent a number of equations in a single equation. You can manipulate a lot of equations at the same time. Basically, you can do things more easily because of matrices, and we'll see that as this unit progresses. Now, for that, operations on matrices needed to be defined. Right, and the only sense it makes is to define operations in such a way that problems become easier. If we wanted to, we could choose to define matrix multiplication in this way. But then what would happen was matrix multiplication would be of no use to us, which means generally matrices would not be of any use to us. You would not be studying them, and sometime in history somebody else would have created another mathematical structure which could have been used to simplify problems, and that is what we would be studying. So why is matrix multiplication not defined this way? The answer is simple. This definition is useless to us. If this was the definition, matrices would not help us in solving problems. The definition which we do have is somewhat counterintuitive and somewhat abstract. So before jumping into the definition, I'd like to show you why we have that definition. In other words, why is that sort of definition useful? So we'll take a slight detour and we'll study a somewhat different topic right now called linear transformations. Right, so linear transformations for our purposes will occur on vectors. We already know what vectors are. From the physics standpoint, they are quantities which have a magnitude and direction. But for our purposes, vectors are matrices which have either one row or one column. One row means it's a row vector, one column means it's a column vector. Right, and I told you we represent matrices by a letter with an arrow overhead. So let's say this is a matrix. Sorry, this is a column vector. Obviously it is a matrix as well, but let's say it's a column vector which has, let's say, columns b1 and b2. It's a 2 cross 1 vector which columns b1 and b2. Let's say there's another vector a with entries, you guessed it, a1 and a2. Now, linear transformations they can occur on functions, they can occur on a lot of things. For our course, they'll occur on vectors. And when you have a linear transformation on a vector, you can guess from the name, it transforms the vector. It changes one vector into another vector. So you could transform this vector in many ways. You could multiply it by 2, then you would get a vector 2a1 and 2a2. That is 2 times a. That is a transformation of the vector. You change that vector into another vector, which is the original vector multiplied by 2. You could add the vector b to the vector a. That would change the vector a. It would become a new vector, which would be the original vector plus another vector. So transformation is basically a change of a vector. You change one vector into another vector, but you don't just change one vector, you change every vector. So for example, if there was a transformation which was represented as being multiplied by 2, so if we applied that on the vector a, then a would become 2a, that is 2a1, 2a2. But every vector in that space would be multiplied by 2. b would become 2b, that is 2b1 and 2b2. Right, so transformations occur not just on vectors but on whole sets of vectors, or what we call vector spaces. And you take a whole set of vectors and you multiply it by something, or you change it in some other way. Another example of a transformation would be, let's say, reflection about the x-axis. If you have a vector like this, and if you reflected about the x-axis, you'll have a vector like this. If you had a vector like this and you reflected about the x-axis, you'd have a vector like this. So reflection about the x-axis could be a transformation in that it changes every vector into another vector. Right. We won't bother with reflection for now. We'll bother with a very specific kind of transformation which is called linear transformations. Right. And linear transformations have a particular property. So if a transformation is represented by, let's say, a function, then if b is the transformation of a, we could write b is equal to, let's say, a transformation. Let's call it t1 for now. We'll introduce another transformation later. t1 times a. So B is T1 times A. Now if B1 is 2 times A1 and B2 is 2 times A2, then this transformation is clearly multiplying by 2 because it multiplies every vector by 2. If B is multiplied by B1 is multiplied by -1 and B2 remains the same in this transformation, then this would correspond to a reflection of A. Right. So B1 is T1 of A1. This is like a function y is equal to f of x. That means A transforms into B. So this is any general transformation which can be represented like this. For every vector A, we have a transformation B. What are functions exactly, right? When you say y is equal to f of x, this is basically a transformation on a number x. For every number x, we get a new number y. If it's, let's say, x cube. For every number x, we get a new number y, which is the cube of x. Right. So for every vector A, we get a vector B, and a linear transformation is a transformation which obeys this rule. T times alpha A plus beta B, where alpha and beta are scalars or numbers. This is equal to alpha into T times the transformation A plus beta into T times the transformation of B. Right, so simple enough. Basically, this is sort of a analogy of a linear function. This is a linear transformation. That means if you have the transformation for the vector A and the vector B, then the transformation for the vector alpha A plus beta B becomes alpha times the transformation of A plus beta times the transformation of B. Right. Now let's look at transformations in a little bit more detail. Transformations, at least for 2 cross 2, for a vector of 2 entries, we were talking about vectors of 2 entries, B1 and B2, can be represented by 4 numbers. Any general transformation. So for example, if this is the vector B and this is the vector A, then we could say B1 is equal to WA1 plus XA2 and B2 is equal to YA1 plus ZA2. Actually, you know what? I'll not use WXYZ because they are generally used for variables. I'll use some other numbers. I'll use PQ, R and S. Now this is the most general linear transformation you can have. B1 goes to something dependent on A1 and A2, and B2 goes to something dependent on A1 and A2. You can verify for yourself. Every linear transformation will be of this form. If it's not linear, then it cannot be represented in this form, but every linear transformation can be represented in this form. So that means B will be equal to PA1 plus QA2 RA1 plus SA2. Now I want to be very clear here. This is a 2 cross 1 matrix. Right, because there's a plus sign, this is just one entry. This is a matrix like B1, B2 or A1, A2. Right, it only has one column. So if B1 is PA1 plus QA2 and B2 is RA1 plus SA2 for some numbers P, Q, R and S, then B would be this thing and A would be this thing. Right. Now, if a linear transformation can be represented by 4 numbers, then it makes sense to try to represent it as a 2 cross 2 matrix. Right, if we are representing vectors having 2 entries by row or column matrices, then it makes sense to represent it by a 4 cross 4 matrix. And the statement B is equal to T times A, where T being a function of A, should now be replaced by B is equal to TA. This is what we want. Okay, we want every transformation, every linear transformation to be represented by a matrix, and then what we want is the new vector to be represented by the matrix times the original vector. So the equation would be B is equal to, let's remove this for now, B is equal to PQRS times A, which is A1, A2. Right, and that should come out to be equal to PA1 plus QA2 RA1 plus SA2. I'll just repeat what we've done till now for clarity. We wanted representations of a linear transformation. If you have a vector A which has entries A1 and A2, and you make a linear transformation to the vector B with entries B1 and B2, every linear transformation can be represented in this way for some suitable numbers P, Q, R and S. Right. So once we've done that, instead of writing B is a function of A, we would simply want to write B is the matrix of this transformation multiplied by A. So instead of applying the transformation to the vector A, you multiply the vector A by the matrix corresponding to the transformation. This will make things easier, trust me. Right now we are doing things which eventually will make things easier. Right. So from this we get one small rule of what we want a transformation to look like. I'll just write that rule in this corner of what we want a matrix multiplication to look like. Whatever the formula for matrix multiplication should be, that should involve one thing, which is PQRS multiplied by A1 and A2 should be equal to A1 plus QA2 RA1 plus SA2. If this is true, now this is only for a 2 cross 2 multiplied by 2 cross 1 matrix, which gives a 2 cross 1. So it's not a general rule, but whatever the rule for matrix multiplication we define, we would like it to follow this pattern. Right. Now let's look at another thing which we would want a matrix multiplication to look like. So now let's say you have two transformations. You have B, which is equal to T1 times A. You have B is equal to B1, B2. You have A is equal to A1, A2. And you have the transformation T1, which is given by, let's say, PQRS. So for this transformation, let's say P was 2 and S was 2. Then B1 would be 2 times A1 and B2 would be 2 times A2. Right. So it would remain the same. It would just be multiplied by 2. So we see that linear transformations indeed can be represented by matrices. Let's take another matrix which would represent another linear transformation to T2. And let's call it LMNO. It has 4 entries, LMNO. Right. Now we can easily write B is equal to T1A, which is what we've written here actually, which can be written as B1, B2 is equal to PQRS times A1, A2. And we know what this should come out to be, a 2 cross 1 matrix with entries PA1 plus QA2 RA1 plus SA2. Right. This is where we've defined matrix multiplication. This was earlier a function on a vector. Now it's a matrix multiplied by a vector. What if we made a transformation to B? And let's say we said C is equal to T2 times B. Now I'm not putting the bracket because it's now not a function. Now it's a matrix. That would mean C1, C2 is equal to LMNO times B1, B2. But we can substitute B1, B2 from here. It would be LMNO times PQRS times A1, A2. Right. So here we can write it as is equal to T2 times T1 times A. And what we would like to do is represent it as T3 times A, whereby saying T3 is equal to T1, T2. So earlier it was a matrix and a vector. Now we are actually seeing what matrix multiplication should look like. We want matrix multiplication to look in such a manner that when you apply a transformation to a vector and you apply a second transformation to the transformed vector, the new combined transformation should look like a matrix which is the product of the matrix representing individual transformations. That's it. That's a long statement. I'll repeat it, but that's the rule. If we have transformations represented by matrices and B is a transformation on A and C is another transformation on B, which means it is a transformation on A, then we want the final transformation to look like the product of the two transformations. Okay, Now I'll write this line again. What we wanted is C1 C2 is equal to LMNO PQRS times A1 A2. Right, but if you actually calculate the value of C2, I suggest you do it. You already know B1 is equal to PA1 plus QA2, and you know B2 is equal to RA1 plus SA2, and you know C1 is equal to LB1 plus MQ1, and C2 is equal to this is B2, NB1 plus OB2. Then you can substitute B1 and B2 from the upper side, and you can see it's equal to L times PA1 plus QA2 plus M times RA1 plus SA2, and this is equal to N times PA1 plus QA2 plus O times RA1 plus SA2. You simplify it and you collect the A1 and A2 terms. What you'll get is this is equal to LP plus MR times A1 plus LQ plus MS times A2. This is C1, and C2 is equal to NP plus OR times A1 plus NQ plus OS times A2. This is it, and this should be equal to C is equal to T3 times A, right? So that is the terms A1 A2 and B1 B2. So ultimately what we would want is T3 to have entries LP plus MR, LQ plus MS, NP plus OR, NQ plus OS. This is it. We'll show you a better way to remember it in a second, but this is what matrix multiplication is. If this matrix and this matrix, now see, we've taken completely general 2 cross 2 matrices. If you multiply these two matrices and you define the product, remember we are just trying to define the product. If you define the product as this 2 cross 2 matrix, then you can represent transformations by matrices completely consistently, where you have no error. You apply one transformation to a matrix, you'll get the vector B. You apply the other transformation to B, you'll get the vector C. Or you can simply multiply the two matrices first, get T3, and then apply that transformation. That would make sense if T3 was equal to this. Right. So we've got two conditions we have on what we want the matrix multiplication to be defined as. This is one, and then we already had PQRS times A1 A2 should be equal to PA1 plus QA2 RA1 plus SA2. So as long as our definition of matrix multiplication follows these two rules, we can represent matrices by number. We can represent transformations by matrices. So we've done a lot in the past few minutes. Let's go back to the original problem. All this was done to show you why this complex definition was needed. See, these entries are not L into M, L into P, M into Q, N into R, and O into S. These are some complicated entries. L times P plus M times R. That's a complicated term. So the matrix multiplication definition would be complicated. If I directly showed you the complicated definition and I said you should remember it, you would have remembered it, but you would not have understood why we do it. This is why we do it, so that all this machinery we can use. Now, just for a moment, look at the screen and look at how many numbers we have. Look at, we have ALP, we have many complicated equations. Wouldn't it be so much easier if we could just write these equations as B is equal to T1 times A, C is equal to T2 times B, which is equal to T2 T1 times A, which is equal to T3A. This equation contains as much information as the whole screen once you define the appropriate quantities and the appropriate operations. So this is where the power of matrices comes into play. We can use equations like this very fast, and you'll be using them along the courses. But right now we see that for this to be true, we have to define matrix multiplication in a complicated way. So a matrix C is equal to a matrix A multiplied by a matrix B in a very special condition. That means they don't have to be of the same size, but there's another broader condition on them. If A is an M cross N matrix and B is an R cross P matrix, then C is equal to AB is defined if and only if N is equal to R. M does not need to be equal to R, N does not need to be equal to P, but N needs to be equal to R, and then C is a M cross P matrix. Okay, so if you are multiplying a matrix A and a matrix B, if this is 2 cross 4 3 cross 4 matrix, then this has to be a 4 cross something matrix, let's say 5. These two numbers have to be the same. The number of columns in the first has to be equal to the number of rows in the second. And then C is a matrix whose entries CJK are defined as CJK is equal to summation L is equal to 1 to N, which is the number of columns in A or the number of rows in B, AJL BLK, or summation, or just let's write it explicitly, AJ1 B1K plus AJ2 B2K plus dot 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 dot. So the entry in the jth row and kth column of the product is not AJK multiplied by BJK, which is what you would expect if you were just following the previous patterns. It is the sum of AJL BLK. What is AJL? It is all the entries in the jth row. L keeps changing, but J is constant. So CJK means take all the entries in the jth row, multiply them with the corresponding entries in the kth column, and add them up. Right. Here J lies of course between 0 and M, and K lies between 0 and P, M and P. Right. It is sometimes also called the multiplication of rows into columns, because notice what these terms are. AJ is the jth row vector of A, and similarly BK is the kth column vector. And what is this vector? Dot product with this vector. Multiply each entry together and add them up. Right. So just to show you a small example, let's just take the previous example but extend it to a 3 cross 3 matrix. A, B, C, D, E, F, G, H, I. Let's take one more actually. J, K, L. So this is a 4 cross 3 matrix. Can you multiply it to a 2 cross 2 matrix? M, N, O, P. No, you cannot. Because if this has 3 columns, this has to have at least 3 rows. Q, R. Now this is a 3 cross 2 matrix, and you can multiply them. 4 cross 3 matrix multiplied by 3 cross 2 matrix. Now notice this peculiarity. They don't have to be of the same size. In fact, they could be of completely different sizes, and yet it would be valid to multiply them, as long as this rule is followed. The number of columns in this is equal to the number of rows in this. Now the product of this would be a 4 cross 2 matrix. So I'll just write down the entries first. Yeah, these would be entries. It would be a 4 cross 2 matrix. That is in the definition. With the entry on the second row, first column. Let's take this. This is the second row, first column. So this is C21. That would be equal to A2 dot B1. The dot product of A2 and B1, or the previous term which we wrote, you could see A21 B11 plus A22 B21 and so on. Right, in AJL plus ALK, AJL times BLK, that term. So the entry in the second row and first column, you take the second row and you take the first column and you take the dot product of them. D times M plus E times O plus F times Q, that is the dot product of these two. So DM plus EO plus FQ. You notice the complicated definition? This is why I showed you why this definition is useful first, and it will be useful. You want the entry in the third row and the second column. Take the third row and take the second column and take the dot product. GHI dot product with NPR. GN plus HP plus IR. Right, just one more. You want to take the fourth row and first column, take the fourth row, take the first column. Now notice, if this had three entries in the columns, three columns D, E, F, but this had only two M, O, then you could not take the dot product. For this dot product to be consistent, the number of columns in the first has to be equal to the number of rows in the second. Right, so this is formally the definition of matrix multiplication, but it has some unusual properties which I'd like to show you. One of them, the simplest property, is that AB is not equal to BA. They are not commutative. In fact, in this case, A into B is defined because 4 cross 3 multiplied by 3 cross 2. But B into A is not even defined because you cannot multiply a 3 cross 2 matrix with a 4 cross 3 matrix. These two numbers have to be the same. Right, so it's not commutative. A into B is not necessarily equal to B into A. There are some other unusual properties of matrix multiplication which I'd like to show you now. So the first one we got, AB not equal to B. Not necessarily equal to. It's possible it might be, but not necessarily equal to B. The other is AB is equal to 0 does not imply A is equal to 0 or B is equal to 0, as it is with numbers. If you have 3x is equal to 0, you know that x is 0. If you have xy is 0, you know that either x or y is 0. Doesn't work the same way with matrices. This does not imply A is equal to 0 or B is equal to 0, or even BA is equal to 0. This is the first unusual rule, second unusual rule, third unusual rules. Why I'm listing these rules? After a few videos, we'll see a special type of matrix which would be called an invertible matrix, and for an invertible matrix these results would hold true. So not generally, but they are true for a specific subset of matrices which in multiplication behave like numbers. AB is equal to AC does not imply that B is equal to C, even when A is not equal to 0. Right? If A is not equal to 0, then AB multiplied by AC does not necessarily imply B is equal to C. Right? So this completes our study of matrix multiplication. Ultimately, matrix multiplication is a short topic, and this should have been a short video if I just gave you the definition. Unfortunately, the definition is so complicated and so counterintuitive that you would say, okay, I agree this is the definition, but why is this the definition? Why not something simpler? And it's because of that I told you the concept of linear transformations earlier. So from now, we will be able to represent any linear transformation on a matrix by any linear transformation on a vector by a matrix. Now let me just show you finally one or two specific types of linear transformations so you'll know exactly what I'm talking about. So first of all, what is the identity transformation? That is a transformation which leaves a vector unchanged, right? And it is represented by the identity matrix. So matrix multiplication is a rule which is such that the vector remains the same as it is. So let's take A1, A2, A3 and let's multiply it with the 3 cross 3 identity matrix 1 0 0 0 1 0 0 0 1, and this will give us, this is a 3 cross 3, this is a 3 cross 1, 3 and 3 are the same, the outside are 3 and 1, so it will give us a 3 cross 1 matrix with 3 entries. What is the first entry? this multiplied by this. 1 A1 and these two are 0. So A1. What is the second entry? This multiplied by this. 0 times A1 plus 1 times A2 plus 0 times A3. So A2. And this is A3. So you see that the identity matrix really does represent the identity transformation, which is a transformation in which there is no change. Another very important transformation is a rotation of the axis about the z direction, right? And this thing happens quite frequently in modern physics, where linear algebra and matrices are actually used very often, and it is something which actually makes things quite simpler. So let's say we have our original set of axes, and let's say we tilt them by a little bit, rotate them by an angle theta. So this was our original set of axes x and y. Let's change them to x dash and y dash, which are tilted by an angle theta. Now there is a point here. Let's call that point x1, y1. What does that mean? That means that the perpendicular to here, to the x-axis, has the total length y1, and perpendicular to the y-axis has a total length x1. Right, therefore the coordinates are x1, y1. Now with this axis, the perpendicular to the x-axis and the perpendicular to the y-axis actually have different lengths. They are not x1 and y1. Therefore this same point in this different coordinate axis would have a different coordinate set of coordinates. Just as a simple case, if you have this point, let's say it's initially 3, 0. If you rotate the axis by 90 degrees, that means initially this was x, this was y. Now you make this x and this y. Then the coordinates would become 0, -3. Because now the x coordinate would be 0, y coordinate would be -3. So the same point, when you change the coordinates, will have a different set of coordinate values. Right, and our goal is to find the new set of coordinate values. So x1, y1 we'll say is the vector A, x2, y2, the same point we'll say will be the vector B, and we want to find the transformation t such that B is equal to t times A. Well, that's simple enough. We can do it by a little bit of geometry. This is theta. This is theta. So I'll do the x1, you can do the y1 on your own. I'll do the y1 actually, this one. So this distance is x2, y2, sorry. This total distance is y1. So I think you can see from this figure, let's call this distance alpha. So because this angle is 90 degree, y2 is equal to y1 minus alpha times cos theta. Right, this side is y1 minus alpha, which is the hypotenuse. Now what is alpha? Alpha is, what is this side? This side is x1. So alpha is x1 tan theta. Right, so from that we get y2 is equal to y1 minus x1 tan theta times cos theta. Or the result you get is y2 is equal to minus x1 sin theta plus x2 cos theta. Try to do x2 for yourself. What you'll get is x2 is equal to, sorry, this should be y1. x1 cos theta plus y1 sin theta. Hang on. I think I made a mistake. This is y1 and this is minus x1, right? Minus x1 sin theta plus y1 cos theta. My bad. Yeah, so minus x1 sin theta plus y1 cos theta. So we've got x2 in terms of x1, and we see now that the rotation is also indeed a linear transformation because we can represent it for every theta in this form. Now notice what this is. This is actually x2 y2, which is b, is equal to t times a, where t is cos theta sin theta minus sin theta cos theta. Sorry, t. Right, and this is generally referred to as RZ theta, or the matrix for the rotation about z axis by an angle theta. It's different for each theta, But you see, if you rotate the matrix by an angle, the axis by an angle theta, and you multiply it by x1 and x2, x1 and y1, what do you get? x1 cos theta plus y1 sin theta is the first entry, minus x1 sin theta plus y1 cos theta is the second entry. So we see that this is a very specific transformation, a rotation of the axis. But if you rotate an axis by an angle theta, rotate the xy plane rather by an angle theta, that can be represented by this matrix. Right. So next time, now this is the first time actually where you now see the advantage of matrices. Next time you see anybody rotating the xy plane by an angle theta, you can just multiply every vector by this matrix, and the new vector will give you the new coordinates of that vector, or the transformed vector. Right. So this completes matrix multiplication. Thank you.